Second order differential equations consists of two parts that are complementary function, which we call yc, and particular integral, which we call yp. So the complete solution y is equals to yc plus yp. We are going to see how to find out yp when our case is such that fd is equals to e raised to the power mx into v, where m is a constant and v could be an algebraic equation or a sine or cos function. For example, our given question is d square minus 5d plus 6 whole into y is equals to e raised to the power x into sine x. Here the term v is sine x. To find out the complete solution to this equation, we would need to figure out yc and yp. For yc, we would take right hand side equal to 0, so this would make our equation. This gives us an auxiliary equation. Now we'll solve this equation and find the roots for d. So the roots for d come out to be, so the roots are 2 and 3. Since the roots are real and distinct, our yc equation would become c1 e raised to the power 2x plus c2 e raised to the power 3x, where c1 and c2 are constants. Now we have figured out yc. Now we have to find out yp. For yp, we change it into a form of 1 upon function of d into e power x into sine x, where our function of d would be d square minus 5d plus 6. This function of d was given in the question. Now we solve this by first solving for the exponential term, which gives me, so the rule here is when we solve for exponential term, the coefficient of the variable in the power of exponent is to be added with d. Here the power of the exponent is 1x, so the coefficient is 1, so we add 1 with d. Simplifying this equation gives us ex into 1 upon d square minus 3d plus 2 into sine x. Now we solve for sine x, just like we solve in the case when f of d is equals to sine x only. So d square will be replaced by minus a square, where a is the coefficient of the variable with sine function. In this case, the variable coefficient is 1. So minus a square will be equal to minus 1 square, which is equals to minus 1. Now substituting d square with minus a square, we get ex into 1 upon minus 3d plus 1 into sine x. We cannot solve with d in the denominator. According to the rule, we need d square in the denominator, so we can replace it by minus a square again. For that, we multiply the term with the denominator's conjugate. So multiplying and dividing the term with its conjugate, we get e power x into sine x plus 3d sine x whole divided by 1 minus 9d square. Now we have a d square in denominator, and this can be replaced with minus a square, which is minus 1. So we replace d square with minus a square. we get ex into sine x plus 3d sine x upon 10. We get ex into sine x plus 3d sine x whole upon 10. Since we know that d represents d upon dx, which means differential, so our term 3d sine x, this will be differentiated with respect to x, which gives us ex dot sine x plus 3 cos x whole divided by 10. Now since we have eliminated all the d terms, this is our final equation for yp. So our yc is c1e raised to the power 2x plus c2e raised to the power 3x, and our yp is ex divided by 10 into sine x plus 3 cos x. So our complete solution would be yc plus yp. So the answer is y is equals to c1 e2x plus c2 e3x plus ex upon 10 into sine x plus 3 cos x. And this is how you solve an equation when the case is function of d is equals to emx dot v, where v could be an algebraic function or sine or cos function. Thank you.